Hello and welcome to this video. So it's a video after quite some time, almost a year, because I was busy with my jobs and really did not get much time. And sometimes I need to think about whether I want to continue making YouTube videos or not, but it always turns out that I have to come back to this. So I will try to upload these videos regularly henceforth. Not a promise, but I will try. So as always, we will solve 10 problems of complex numbers. So without further ado, let's get started. As always, I'll say that when I'm reading the problems, uh, pause the video and do not look at the solution and try to solve the problem yourself. If you cannot solve the problem yourself, only then look at the solution. Now, some of the problems in this video are going to be a little bit lengthy. So uh, the video will be a bit longer because of that. So there are two problems which are lengthy. One is this calculation of orthocenter. Another would be the calculation of circumcenter. So this problem asks us to find the orthocenter of a triangle whose vertices are represented by Z1, Z2, Z3, and these are two values of orthocenter which we have to obtain. The values are Z1 A sec A plus Z2 B sec B plus Z3 C sec C divided by A sec A plus B sec B plus C sec C. Or alternatively, we have to prove that this is equal to Z1 tan A plus Z2 tan B plus Z3 tan C by tan A plus tan B plus tan C. So this is the diagram. We have a triangle ABC. The length of the sides are A, B and C. As you know, the orthocenter is the meeting point of altitudes or perpendiculars to the opposite side. So one of the perpendiculars is AL, the other perpendicular is BM, and their meeting point is H. So H is our orthocenter. So let's see how we calculate this. So if you see BL by LC, BL by LC will be C cos B by B cos C. So BL, if you see in this triangle, triangle ALB, this is C. This angle is 90 degree. So we take cos B will be BL by AB, that is base by hypotenuse. So BL will be C cos B. So similarly, LC, you can figure out that LC would be B cos C. Okay. So if you see LC in this triangle, and you take cos of this, it would be hypotenuse and base. So base by hypotenuse. So LC would be B cos C. Alternatively, we can take cos C to numerator as sec C and cos B to denominator as sec B. So the point L will divide BC internally in the ratio of C sec C and B sec B. So from the section formula of complex numbers, we have the coordinate of L as Z3 C sec C plus Z2 sec B sec B by C sec C plus B sec B. Now AH by HL is equal to area of ABH by HBL. So we see how we arrive at that. So this is AH and this is AL. If you look at this triangle, the area would be AL by AL into BL into half of BL into AL. And the area of this triangle would be half into BL into HL. So you can acquire the area of this triangle. So from AH, if you subtract HL, you will get H, and that would be our area. So you can see from the extended figure also that that would be true. Now, clearly, area of ABH would be half into AB into BH into sine angle of ABM. That is from the formula of area of a triangle. And area of HBL would be half of BL into BH into sine MBC. Now ABM, if you see in the diagram, that would be 90 degree minus A, and MBC would be 90 degree minus into C. So this becomes BH will be cancelled out, AB would be C, and BL we have already deduced as C cos B. So that would be C cos A divided by C cos B into cos C. Now C gets cancelled out and we multiply and divide with A. Now A we can write as B cos C plus C cos B. So we arrive finally at this value. Okay, that is B sec B plus C sec C divided by A sec A. So you see from here we divide by cos B cos C. So this became B sec B. This became C sec C. This cos A goes down. It becomes A sec A. So from this you see that H will divide AL in the ratio of B sec B plus C sec C divided by A sec A. Now once we know the ratio and we have the coordinate of A, we have coordinate of L, we can figure out H as Z1 A sec A plus Z2 B sec B plus Z3 C sec C divided by A sec A plus B sec B plus C sec C. Now if you observe, this is a cyclic relationship, that is symmetrical relationship. So similarly we can figure out that for B and C, that is if we look at M and if we draw perpendicular from this side, we will arrive at the similar value, that is same value, not similar, same value we will arrive at. Thus we have this orthocenter as given. Now from this formula what we can do is we can write A as K sin A and B as K sin B, C as K sin C, and then what we do is we cancel out K, okay, and then sin A into sec A will become tan A, sin B into sec B will become tan B, because sec is 1 by cos and sin into 1 by cos will be sin by cos, that will be tan. So thus we will have both the formulas for orthocenter. Now problem 182 says that if the vertices of a triangle are represented by Z1, Z2 and Z3, then we have to show that the circumcenter is given by Z1 sin 2A plus Z2 sin 2B plus Z3 sin 2C divided by sin 2A plus sin 2B plus sin 2C. So this is the diagram. We have the circumcircle of triangle ABC as shown in the diagram. This middle dot is, let's say it is O, which is the circumcenter. So from here OA will be equal to OB equal to OC, which will be the radius of the circumcenter, circumcircle, which is also called circumradius. Now sides are shown as ABC. We have drawn a perpendicular L to side BC from O, and we have extended this median of sorry, not median, the bisector of the angle over here. Since this is the not bisector also, is the straight line OA is extended to D. So if this angle is 2C, which will be because this chord AB makes angle C here on the circumference, then at the center it will make twice that angle, that is 2C. So the angle BOD will be pi minus 2C because this is a straight line. And angle COD will be pi minus 2B. Okay, so let's now go on to the calculation of circumcenter. Now this technique we could have adopted as well for orthocenter, but it's a different technique. So I have presented the alternative technique to find out the circumcenter. You can use this to find the orthocenter as well. So we can say that BD by DC is equal to half BD into OL divided by half into DC into OL. So we have just multiplied and divided with half into OL. Now this will be area of triangle BOD, this will be area of triangle COD, which is alternatively half into OB into OD into sine pi minus 2C, half into OC into OD sine pi minus 2C. That is sine 2C by 2B. So from this, you see that D divides BC internally in the ratio of sine 2C is to sine 2B. So D can be written as Z3 sine 2C plus Z2 sine 2B divided by sine 2C plus sine 2B. Now looking at the required formula for circumcenter, we arrive at a ratio sine 2B plus sine 2C is to sine 2A, which will give us the required formula. This is by observation we can figure out. Okay. So once you figure out this formula, this ratio, the circumcenter is quickly derived here. Now this is symmetrical with respect to ABC. So the other bisectors, that is other straight lines from BO if we produce and CO if we produce further, we will have the similar formula. They will divide the other side in the ratios of sine 2C plus sine 2A is to sine 2B and sine 2A plus sine 2B is to sine 2C. And thus each time we will arrive at the same formula, and thus the formula for circumcenter is derived. Problem 183 says that show that the circumcenter of the triangle whose vertices are given by complex number z1, z2, z3 is given by z is equal to sigma z1 z1 bar into z2 minus z3 divided by sigma z1 bar multiplied with z2 minus z3. So we have the diagram of the center of a triangle, and we have the circumcenter, and if this is O, then it will be at equidistant from all the vertices of the triangle. So since it is at equidistant from each vertex, if z is the circumcenter, then mod of z minus z1 is equal to mod of z minus z2 is equal to mod of z minus z3, because the magnitude of the distance will be same. So we take the first two, we have mod of z minus z1 is equal to mod of z minus z2. So we square that, and then square is written as z minus z1 into z bar minus z1 bar, because if you recall, mod of z square is equal to z bar. Okay. Similarly, on the right hand side, we have z minus z2 into z bar minus z2 bar. So you multiply, divide, solve, simplify, you arrive at this relationship. Okay, is equation number 1. Similarly, if you consider the first and the third as a combination, you will arrive at this equation. Now, if you observe at these two equations, what is it we have to derive? We have to derive z. z1 bar, z2 bar, z1, z2 are given to us. One problem which we have is this z bar. We have to eliminate this z bar. In this equation also, we have this problem. This guy is unknown. So we have to eliminate z bar. So you multiply equation 1 with z1 minus z3 and 2 with z1 minus z2, and you solve it, you subtract it, and then you arrive at the desired result. Problem 184 says that find the orthocenter of the triangle with vertices z1, z2, z3. So this is, we have proved in terms of angles, but this is what we will prove in terms of z1, z2, z3. Now if you see this, H is perpendicular to BC. Okay. So we can say that if the Z is the orthocenter of ABC, then argument of Z1 minus Z divided by Z3 minus Z2 would be plus minus pi by 2. You see, Z1 minus Z would be this guy. It will be this complex number, and Z2 minus Z3 will be represented by side BC. Z minus Z1 will represent AH. So the argument can be either pi by 2 or can be minus pi by 2. That depends on the diagram and the location of the center, because this can be basically, you can consider a mirror image of this, in which case A will be at the bottom, then it will be a different sign of the argument. All right. Now this implies that the value z1 minus z by z3 minus z2 is purely imaginary, because this, if you put in terms of cos theta plus I sin theta, then cos theta will become 0. Okay, it will be only I sin theta which will be true. Now for that case, we can apply the known formula that the conjugate of this complex number will be equal to minus of that complex number. We have this relationship here, and we then take over the bar, we remove the bar and apply it to individual numbers, and we arrive at this. from here you can arrive at this relationship, which is Z1 bar minus Z bar is equal to Z minus Z1 into Z3 bar minus Z2 bar by Z3 minus Z2. And then we consider another perpendicular, that is BH, on this line. And then accordingly you solve, and in that case it would be Z2 minus Z by Z3 minus Z1, which will be plus minus pi by 2, and then you solve, you arrive at this. Now you have two equations, and then you can eliminate Z bar from both, and you arrive at the desired result for the ortho center. Problem 185 says that ABCD is a rhombus described in clockwise direction. So clockwise is like A, B, C, D. Suppose that vertices ABCD are given by Z1 through Z4 respectively, and angle CBA is equal to 2 pi by 3. Show that 2 square root of 3 Z2 is equal to square root of 3 minus I into Z1 plus square root of 3 plus I Z3, and 2 square root of 3 Z4 is equal to root 3 plus I Z1 plus root 3 minus I Z3. So we have the angle CBA is equal to 2 pi by 3. So A, B and C, alright. So this angle will be given by, or rather we can write that Z3 minus Z2 by Z1 minus Z2. So C will be here, B is here, and A is here. So this is BC and this is AB. So this will be given by mod of Z3 minus Z2 by mod of Z1 minus Z2 into cos 2 pi by 3 plus I sin 2 pi by 3. Now, since it's a rhombus, BC will be equal to AB, and therefore we can write that Z3 minus this magnitude will be equal. This BC is equal to AB means this magnitude will be equal, and therefore you cancel out. So you can say that Z3 minus Z2 by Z1 minus Z2 is equal to minus half, which is cos 2 pi by 3, and plus I root 3 by 2, which is sin 2 pi by 3. And thus we have our first desired result. And since the diagonals bisect each other, we have Z1 plus Z3 by 2 and Z2 plus Z4 by 2. So we have Z4 is equal to Z1 plus Z3 minus Z2, and we have the value of Z2 from here, we substitute, and then we arrive at the desired result. Problem 186 says that the points P, Q and R represent the numbers Z1, Z2 and Z3 respectively, and the angles of the triangle PQR at Q and R are both 1 by 2 pi minus alpha. Prove that Z3 minus Z2 whole square is equal to 4 Z3 minus Z1 into Z1 minus Z2 sine square alpha by 2. So we are given that two angles are equal, that is PQR and PRQ are equal, which is equal to pi minus alpha by 2. Therefore, two sides will be also equal. The side opposite to PRQ will be PQ, and the side opposite to PQR will be PR. So the third angle can be found because two angles are known, that will be pi minus 2 into pi by 2 minus alpha by 2, which will be equal to alpha. So we can say that argument of Z3 minus Z1 by Z2 minus Z1 is equal to alpha. That is Z3 minus Z1 by Z2 minus Z1 is equal to PR by RQ cos alpha plus I sin alpha. Now this will be equal to 1. Alright. So we have Z3 minus Z1 by Z2 minus Z1 minus 1 is equal to cos alpha minus 1 plus I sin alpha. Now this becomes, sorry, Z3 minus Z2 by Z2 minus Z1 is equal to cos alpha minus 1 will be minus 2 sin square alpha by 2, and sin alpha will be 2 sin alpha by 2 cos alpha by 2. This comes from trigonometry. Now we square both sides. Okay. So we get Z3 minus Z2 by Z2 minus Z1 whole square is equal to, we take out 2 sin alpha by 2, square that, we get 4 sin square alpha by 2 and cos alpha by 2 plus I sin alpha by 2 whole square. Okay. And thus you solve it further and you arrive at the desired result. Question 187 says that point Z1 and Z2 are adjacent vertices of a regular polygon of n sides. Find the vertex Z3 adjacent to Z2. Z1 is not equal to Z3. So imagine a hexagon. Alright. Now you imagine one triangle formed by taking 2 points the vertex of hexagon and the center. So the side will make angle of 60 degree at the center, which is equal to 2 pi by 6, 6 being number of sides. And the two sides of the triangle, which will be from center to the vertices, will be equal. So it's an isosceles triangle. Any regular polygon will have this behavior. Alright. So if C is the center of the polygon of n sides and A2 and A3 are three consecutive vertices, then angle CA2 A1 will be equal to half pi minus 2 pi by n. This you can figure out from basic geometry. So angle A1, A2, A3 would be pi minus 2 pi by n. Now when Z1, Z2, Z3 are in anti-clockwise order, this will give us Z1 minus Z2 is equal to Z3 minus Z2 e to the power I pi minus 2 pi by n. Because A1, A2 is equal to A3, A2. So from this, we can reduce our Z3 because e to the power I pi is minus 1. So we arrive at this result for Z3. And similarly, for the clockwise order, this relationship can be written as Z3 minus Z2 is equal to Z1 minus Z2 e to the power I pi minus I2 pi by n. Thus, you can find the Z3. Problem 188 says that let A1, A2 to A and B the vertices of n-sided regular polygons such that 1 by A1, A2 is equal to 1 by A1, A3 plus 1 by A1, A4. Find the value of n. So we let O2 be the origin and complex number representing A1 be Z. Then A2, A3, A4 will be represented by Z e to the power I2 pi by n, Z e to the power I4 pi by n, Z e to the power I6 pi by n, and so on. Because as I told, each side will subtend an angle of 2 pi by n on the center. Okay. Now we let mod Z is equal to A. So A1, A2 would be mod of Z minus Z e to the power I2 pi by n. That is mod Z into mod of 1 minus cos 2 pi by n minus I sin 2 pi by n. Now, since mod Z we have taken as A, we write that as A. And this we can write as 1 minus cos 2 pi by n whole square plus sin square 2 pi by n. This modulus of this complex number. So now this, if you solve, you will get A into square root of 2 minus 2 into 1 minus cos 2 pi by n. Now 1 minus cos 2 pi by n will be 2 sin square pi by n. So 2 into 2 will become 4, and 4 when taken out of square root will be 2, and sin square pi by n will be sin pi by n. So we arrive at 2a sin pi by n. So since we have a1, a2 here, and this is a regular polygon, so a1, a3 will be 2a sin 2 pi by n, and a1, a4 will be 2a sin 3 pi by n. Okay. Now we substitute this in the given formula. Alright. That is 1 by a1, a2 is equal to 1 by a1, a3 plus 1 by a1, a4. We substitute this, and then you solve this, and you arrive at n is equal to 7. Okay. So the values of sorry, I lost it. Right, let me go through this and then we will see. So we have this value 2a will get cancelled, so we have sin pi by n into sin 3 pi by n plus sin 2 pi by n is equal to sin 2 pi by n into sin 3 pi by n. By taking LCM and cross multiplication, we arrive at this. Now from here we can write sin 3 pi by n plus sin 2 pi by n is equal to 2 cos 2 pi by n into sin 3 pi by n. This comes from geometry. Now this can be written as sin 4 pi by n plus sin 2 pi by n. Now 2 pi by n will get cancelled here. So we will have sin 3 pi by n is equal to sin 4 pi by n. That is 3 pi by n is equal to m pi plus minus 1 to the power n 4 pi by n. Now if m is 0, the values of m given as 0 plus minus 1 plus minus 2 up to infinity. So this is the general value of this angle 3 pi by n. And this comes from trigonometry. Okay. So if you have not studied trigonometry, you have to just take formula just like that. We will prove this general value when we study trigonometry. Now if m is 0, okay, 3 pi by n is equal to 4 pi by n, that is 3 is equal to 4, which is not possible. Now m is equal to 1, then we have some value of n, which is 7. Now when you solve for trigonometry for general values, usually you should pick the smallest value. So even if other values of further values of m can give us some integral value here, we should not take that. We should take the smallest value all the time. So this would be the smallest value of n, which is 7. Okay. If you try to substitute other values, which are not which you will see that those are not possible. So in the end, you will arrive at the conclusion that n is equal to. Problem 189 says that if mod z is equal to 2, then show that the points representing the complex number -1 plus 5z lie on the circle. So we are given mod z is equal to 2 and z1 is equal to -1 plus 5z. So from here we can say that z1 plus 1 is equal to 5z. So we take modulus of that, z1 plus 1, mod of z1 plus 1 is equal to mod of 5z, and mod of 5z becomes 10 because mod z is given as 2. So 5 into 2, 10. Now this is the equation of a circle with center -1 and 0 and radius square root of 10. This is wrong. This radius is square root of 10, not 10. No, radius is 10 because it would be x1 x plus 1 whole square plus y square is equal to 10 square. So radius is 10. Sorry, I was wrong. Radius would be 10. All right. Our last problem 190 says that if mod of z minus 4 plus 3i less than equal to 2, find the least and the, there is a typing mistake, greatest values of z mod z, and hence find the limits between which mod z lies. So this gives us mod of, this is mod of z minus 4 plus 3i less than 2. So if you look at this in a geometrical way, then this represents a circle with center at 4 comma minus 3 and the radius should be less than 2. So this gives us 5. Mod of this would be 5. So you see how the calculation is done. This value, that is mod of z minus 4 plus 3i, is less than equal to mod of z minus 4 minus 3i. Now this is equal to mod z minus 5. Mod of that is less than 2. So we take out the outer mod and this value becomes -2 is less than equal to mod z minus 5 is less than 2. So the value of mod z will lie between 3 and 7. Okay, this is easy to understand. Consider a sphere. Okay, and the center is at 4 minus 3, and we are given that the radius of this circle will be how much? 5 units. From this we will have circle as 5 units. Now the shaded region is 2, so clearly this is between 3 and 7. Right. So for this session we will have these many problems. I hope you have enjoyed the video and found it useful for your exams and preparation on complex numbers. If so, please subscribe to the channel and like the video because that will motivate me to make more such video, and share it with your friends and whomever you know who like to study mathematics. Thanks a lot for watching the video. See you in the next video. Thank you.